Back, and this is the last tutorial session for this course. And instead of doing MATLAB offline simulation, I thought to put this. This is a specific. It was not in the plan, but suddenly I thought like some of the equipment, because many of you asked, like some of you are developing lab or some of you want to know how Polity works. So basically this is the state of the art real-time simulation platform, you can say. And with respect to that, I tried to link with our course, but it was not fully linked because we could not develop any hydrogen model here. But at least I can give you a link so that in future you can plan the experiments. So one of my master students had developed some grid forming control that we will demonstrate using this real time. But again, I will tell you how to link it. So if I want to inject power to the grid, shall I use fuel cell or hydrogen electrolyzer? I want to use it at a source, fuel cell, right? So this is a single line diagram. If I consider I was using a hydrogen fuel cell, I mean this is not up to the scale, this is my level of drawing, so don't excuse me for that. So hydrogen is a inflow, then using those electrochemical reaction, and then you generate the output DC, and that DC again is not compatible for the DC link for the inverter. So we can put a DC-DC boost. We already discussed this thing. We boost the voltage, and that voltage for grid integration we use a inverter, and you can see the direction of current or power flow, and at the output side we have mostly AC, right? So at the inverter, to avoid the switching frequencies, we use a low pass filter or some kind of low frequency filter, which basically you can use L filter, LC filter, LCL filter depending upon your application. I just give a symbol of ZF. ZF means impedance, so anything you can use filter impedance. And after that I put a breaker, so you can somehow relate to it is a point of connection to my previous lecture. And point of connection you connect to the rest of the grid. Okay. Now grid I represent as a Thevenin equivalent. Thevenin, if you have done network theory, this Thevenin equivalent basically we represent a voltage, Thevenin voltage in series with Thevenin resistance or impedance, and that represents the total grid. So in power system, this model we call as, if I take from here to here, initially if we have a synchronous machine, we call it a single machine infinite bus. For inverter, I am naming it as single inverter infinite bus, okay, SIIB. So this total schematic is an application, what I say, it is a grid integration of a grid forming fuel cell. So this control, if you see, one controller for this power electronics, one controller for this, and grid forming has to be implemented here because this part is connected to the grid. Now due to the limitation of time, what I did, I just assume that everything done here, this DC is fixed DC. I assume that fuel cell reaction happens, DC voltage happens, DC converter control already implemented. I got my goal, I get a fixed DC. So that DC I replaced with a fixed DC battery. Okay. That DC battery, rest of the thing I keep it same. Now what we are going to see here, this inverter along with its controller. This controller I name it as a grid forming controller. Okay. Now what we will do, Opal at, of course more details will be told later. I can give you just a hint. If you see to the table, how many machines you are seeing? Two, right? One is small, one is big. The big one, the version is OP5707. So basically this red dotted thing, okay? That inverter power circuit model we are building in using one type of simulator, which is OP5707. And the small box you are seeing, that is basically a DSP controller, okay? So that DSP controller is inside another simulator. that we call it as OP8666. So these two OP stands for their opality products. So these two OP will talk to each other now through this feedback and control. That's what we are going to see. So this is one of the schematic of one of my master students. So that model we are going to show you. And the important thing is you have to understand, rather than control, how to use these two machines and what are the hardware connections you need to do, what are the software connections you need to do. For that we have brought up an expert from Opalati. With me I want to introduce Mr. Shiva Kumar. He is a field application engineer from Opalati working in Bangalore office. So he will be demonstrating more about these machines and how to implement the model and controller using these two. Over to you, Shiva. Both inverter and control in the same simulator, I can call it as a model in loop. I can do that, but that is the simplest way. But purposefully I am doing controller, hardware and loop. I don't want to put both model and control in same simulator. I want to put model in one, controller in one, so that it makes a loop actually, as you know, control hardware in loop. But my controller will be in a different hardware, I will say, and they will communicate. So basically 5707XG and 8666, they will communicate and control the inverter for grid integration.
Yes.
Okay.
Thank you.
Thank you. You can see.
Opalati Technologies. So first, for the next 15 to 20 minutes, I'll just go ahead with a short PPT presentation, which explains you about what is exactly a real-time simulation and why do we use Opalati and where are the applications we find useful with this equipment. So I'll go ahead with this PPT for the 15 minutes, and after that we can go ahead for the demo. Okay, so like Opalati, we are the persons who are into developing real-time digital simulators, which is used for rapid control prototyping and hardware in loop based validations. So these are some of the software toolboxes which we have. I'll RT Lab, eMegaSim. So I'll quickly tell you what is what in the upcoming slides. So we speak about real-time simulations. What is exactly a real-time simulation and how real-time simulation is different from a normal offline simulation. So I'll try to address that query. So real-time simulation means it should be fast enough in the sense whatever time step you give in your simulation, that time step needs to be respected in real time. To put it in other words, if you are giving a stop time of 10 seconds in your simulation, the simulation has to stop in 10 seconds. It should match your wall clock. So that is what real-time simulation is all about. The runtime of the simulation should match your wall clock. If it is running for 30 seconds, then in wall clock also it should be showing 30 seconds. Time simulation is all about. Real-time simulation means it should follow the runtime of your simulation should follow real clock. So let us say if you are giving a time step to the model in MATLAB, that time step has to be strictly followed. And also if you are like whatever runtime you see on the simulation, that runtime should have a sync with your real wall clock. So if it is 10 seconds, it has to be 10 seconds, and if it is 20 or 30, whatever runtime when you have in your simulation, it has to match the wall clock. So that is another way of explaining real-time simulation. Let us say you have some controller and you have some real plant. You'll have some tasks running, like let us say each simulation will have a fixed time step. So in a given fixed time step, the simulation should do some measurements, do some computations, and it should give out some commands. So every time step this should happen, like for every iteration this will be repeated. So real-time simulation means all these measurements, computations and command, whatever task a simulator does or whatever task your CPU or your simulation does, it should be done within your specified time step. So let us say your simulation model is something which is very complex. Let us say you are running some 118 bus system and you are running at 10 microsecond time step. So 118 bus system is so complex that it will be difficult for your CPU to do those computations within the 10 microsecond time step. So that computation might exceed your time step, and this phenomenon we call it as overruns. In real time simulation, you should not have this overruns. All whatever your computation measurements, whatever your CPU does, it should be done within your fixed time step. This is what real time simulation is all about. So there are two ways to explain it. One is it should follow your wall clock. Second one is it should follow your fixed time step. Whatever time step you have in your MATLAB simulation, that has to be respected hands down. So yeah, this is what real time simulation is all about. Why do we need this? Why do I want a simulation to be executed at a speed which is equivalent to wall clock? All those stuffs I will explain. So this will come into picture whenever you are trying to introduce your simulation to the external world. Let us say you want to test your simulation with some external hardware like you have here. You have a controller here. If you want to test your simulation with some external controller or some external plant, the first thing is you should run your simulation in real time. So that is the first step. Again, the hardware in loop validation, rapid control prototyping validation, all those stuffs will need a real time simulation to be executed. So we have a real time simulator here. You see this big box here. This is a high end variant. We do have more compact simulators as well. So what does this simulator exactly have? So basically it will have few IO cards. Let us say you have some device under test. Let us say you have some controller, or let us say you have some inverter, or let us say you have some power system relays or whatever. So you will have a device under test, and that device under test will be linked to the simulation which is running inside this simulator. It will be linked through IOs. You will have analog in, analog out, digital in, digital out and stuff. So the simulation will be running inside a real time processor, and you will also have a host PC connected, like the way I have my laptop connected to the simulator. So your host PC will have the simulation model, and from the host PC you will dump the model onto the simulator, and it will be executed onto this processor. So you can also have an IO expansion unit. So let us say you have a multi-level inverter to control, and normally our simulator comes with 32 channels or 64 channels. And if you say, let us say it is not sufficient, let us say your multi-level inverter has some 40 or 50 switches, and if your digital output is not sufficient, then you can have an IO expansion unit to match the IO count. So it's not only you can communicate with your device under test through IOs, you can also have communication protocols. Let us say in a smart grid application, if you have some PMU or if you have some RTUs with you, you will need communication protocols like C37, IEC, DNP3, all those stuffs. So we do support those kind of communication protocols. So yeah, this is what a real-time simulator has. We do have an FPGA inside it. The role of FPGA is to configure the IOs. That is one role, and other role is we do have one solver. We have a software toolbox which helps you to run power converter models directly onto the FPGA. So that will running models onto the FPGA will help you to achieve high switching frequency simulations, and you will be able to achieve nanosecond time steps. So yeah. So in Opalati we have a workflow. So we start with a model based design in a simulation. So that simulation you will generate a code through one of our softwares, and you will dump that code onto the real time simulator, and this simulator will be connected to your device under test, and you will do the test. And if you want to do some tweaks to the model design, you again come back to the model design, do some tweaks, and you completely do this steps multiple times until you get the right results. So we start with a simulation model. That is what is the basic idea. We run the simulation model. The MATLAB model will be executed onto the simulator, and the simulator will help you to link your simulation with the external world. So yeah, these are types of real-time simulation. Some of you might already know. We have a model in loop mill, we have hardware in loop hill, we have RCP, rapid control prototyping, and we also have PHIL. I'll slowly tell you what is what quickly. So model in loop means So we'll go through a lot of stages of validation, like whatever research idea you have before you go for the final hardware implementation. We normally take your idea through different stages of validation. So the first stage of validation is this model in loop, where broadly you will have a controller and plant in your simulation. So everything will be simulated. That is what model in loop is all about. You will not have any interaction with the external world or external equipment, whatever you have. So this is the proof of concept for your research. It is like a preliminary studies, and you will be able to do a kickstart your research with a model in loop validation. So next we'll slowly try to introduce your simulation to the external world. The next stage of validation will be rapid control prototyping, where you'll have the controller simulated inside and the plant will be outside. So if it is an induction motor drive, let us say, you'll have the control for the inverter inside, and you'll have a real inverter and motor outside. So this stage of validation is called rapid control prototyping. This will help you to refine or fine tune your control algorithms when it gets connected to a real equipment, right? So this is what is RCP. Next is hardware in loop. In hardware in loop, it is the other way around. You have the controller outside, you have a real controller, and you'll have a simulated plant, like here. I have a real controller here, and I'll be having a simulated plant inside the simulator. So this will help you to prepare your controller for the final tests. Before this controller goes for the final tests with the hardware, you can test this controller with a simulated plant. You can test it for a lot of other scenarios, like different adverse load conditions or some fault conditions. You can test your controller, and then you can go for the final hardware implementation. So this is hardware in loop. We do have one more stage of validation called power hardware in loop. So in all the previous cases, whatever I said was whatever interaction you have between the simulation and the external world, that was a signal level interaction. So even here, I only have a signal level interaction between the controller and plant, between the controller and the simulated plant. But in power hardware in loop, you will have a power level interaction with your device under test. For example, let us say the device under test could be some traction inverter, let us say. So let us say you have a traction inverter which is going into an EV. So that traction inverter, it needs to undergo a test, it needs to undergo a power hardware in loop test with a simulated motor for different adverse fault scenarios and adverse speed conditions, let us say. Then you will need a power hardware in loop validation. You will need a power amplifier between your simulation and the DUT, which helps you to connect your simulation to the DUT at power level. Let us say you have a simulated motor, and you want that simulated motor to exchange power with a real inverter which is outside, let us say. So that will not be possible with just the simulator and your DUT. You should have a power amplifier in between, which helps you to do a power level interaction between your simulation and your DUT. So this is what PHIL is all about. Yeah, this is more a complex setup, and it is a more costlier setup as well, but still this helps engineers to test their DUTs before it goes for the final field implementation. So yeah, this is what PHIL is all about. So I spoke about model in loop, I spoke about RCP, rapid control prototyping, and I spoke about hardware in loop, and this power hardware in loop. So these are the different areas or applications where you will use this real-time simulator. Okay. Yeah, so I'll go ahead. So apart from this real-time simulator, we do have lot of software toolboxes which helps you to enhance your simulation experience. You can see we have EFPGA-SIM, as you can see. As I told earlier, EFPGA-SIM toolbox helps you to run your power converter simulation inside FPGA, and we have eMegaSim for power system simulations. And we have ePhasor Sim for, again, it is for power system simulations, but ePhasor Sim will help you to import third-party power system models like PSSE, Power Factory and stuff. And we also have HyperSim. So all the other toolboxes, it needs MATLAB Simulink, but HyperSim is like a standalone simulation software made by Opal to do power system simulations again. Yeah. Depending on the application, we'll advise you which software toolbox will suit you. So These are some of the application areas where you will find real-time simulation. So yeah, now I'll go ahead with the demo which we have planned. I'll just show you the model. I'll show you the model. Let us say you have a simulation model and how to run that simulation model into a real-time simulation, into this real-time simulator. All those steps I'll quickly go around and I'll tell you.
Couple of questions from my side. Please ignore my ignorance about this thing. So I know very little about this. So I'll make some mistakes.
No problem.
First of all, is that you are talking about this PHIL. Now, when you're talking about connecting a hardware that may be a induction motor or other motor devices, so you will be invariably using a PHIL there, because for this DSP controller that can be connected easily to the Opal RT. But when you are using directly a motor or any other heavy devices, those should be communicated to it through a power amplifier. So PHIL is a much more normal way of working.
Not necessarily. Induction motor drive, let us say. So you have an inverter and you have a motor. So, and if you want to control the inverter through Opal RT, then you don't need, it's not like you will need a power amplifier in between. That is still a signal level interaction. So you will just have to take the voltage signals, give it as a feedback to the analog inputs, and it will further give out the PWMs to control the inverter. So this is still a signal level interaction, even though you have a motor and inverter. This is still a signal level interaction. Power level will come into picture when you let us say so let us say you have an inverter and you want to link that inverter with a simulated motor, and that simulated motor, whatever changes you see on the motor, you should see the change of that motor at power level with the inverter. So these kind of simulations will need a power amplifier in between. The other case which I said, you have only the controller inside the simulation, so it is not necessary that you need a power level connection between your plant and controller. So it basically depends on the application. It's not like you always need a power amplifier if I have an inverter or motor. It depends on the application.
Sir, one FPGA part in this Opal RT. So
yeah,
what?
So there are two roles for FPGA here. So one role for FPGA is to control your IO device. Let us say you want to generate 100 kilohertz PWM, then you need FPGA. And other role is to run the plant model. Let us say you have a power converter which needs to be executed at 100 kilohertz. Then 100 kilohertz simulation will demand nanosecond time steps. So nanosecond time step will be difficult for your normal CPU or processor to achieve. So in that case, we will need the FPGA into picture, and we will run your power converter onto the FPGA, and that will help you to run more faster simulations and test it with the controllers and stuff.
Okay, thank you, sir.
I'll quickly go around. We have a plant running, as sir explained initially. We have a grid forming inverter in MATLAB. So that is executed in this 5700 simulator, and we also have one control algorithm for this inverter inside this controller, which is placed outside. So I'll quickly go around. First I'll go around with the plant model, and then I'll show you the plant model. I'll tell you how to execute the plant model into real time and all those steps. Next one, I'll show you the controller model, and I'll also explain you the hardware connections involved between both. Oh, okay. Hardware connections I'll parallelly explain when I show you the model. So fine. So now I have the plant model here. So whatever plant model you are running or whatever simulation model you want to run in Opal RT, you do have some small procedures to run it. Let us say you already have a simulation model which is already validated in offline, your results are perfect. And if you want to run that simulation model into the Opal RT, you do have some very minor modifications which needs to be done to your simulation. So anyhow, we'll be able to guide you guys if you are doing that. But anyhow, to put it in a brief way, the top level of your simulation should have only subsystems like what I have here. One subsystem is called the master, and the other one is the console. Master is a subsystem which will have your plant, whatever thing which is going to be computed inside the CPU, that will go into the master. And console is something which will help you to interact with the simulation when you are running it. So the console will have all the scopes and some control variables. If you want to change any parameters in the simulation, all those steps will have in the console. So now I'll show you the master, and also you should always make sure that your simulation is made with fixed time step solver. So here, if you go to the model settings, so here you have the solver type. In MATLAB you have two options, one is the variable step solver and other one is the fixed step solver. So whenever you are running a real time simulation, you should always make sure that your model is developed in fixed step solver. So that is one thing. And here you can see the plant. I have a DC source here, and I have this inverter which is acting as a grid forming inverter, and I have an LC filter here, and I also have the infinite bus. We also have few a resistive load here to connect and disconnect, and we also have one fault system here which will help you to insert fault and see how your controller is behaving. So now this is the plant. Now you have the controller outside. To this inverter which you have here, the PWM for this inverter is going to come from this controller which is outside. So to do that, we need to first send the feedback signals from this simulation model to the controller which is outside. So you need to configure analog outputs on this simulator to send the feedback signals.
With that, so the inverter is basically a 3-leg inverter, 2-level 3-phase. Okay, and you have there are 6 switches, and we discussed DC-DC converter. This switch pulses has to come from the controller. Okay, thank you. Controller, whatever you see is the power circuit, and we call it, in control system language, we call it plant.
To link the external controller with this simulation, you need to send some the feedbacks to the controller, right? So currently your current controller will need the 3 grid voltages and also the currents which is after the filter and before the filter. So you have a filter here. So all these feedbacks we need to send. So I am adding the measurements inside. I am adding the current and voltage measurements in the model, and you still need to do some signal conditioning to meet, because our analog output is rated. Our analog output you can send only plus or minus 16 volt, and also this controller can take a plus or minus 10 volt for taking the feedback. So accordingly, you do the signal conditioning here, and you send it to the analog output. So here we have this analog output here. This is an analog output block which helps you to configure the analog output which you have in the simulator. On the back side of the simulator, we have the analog output. Maybe in the break you can come and see the connections once. So from the analog output, I will connect all the feedbacks to this to the analog input of the controller through this connector. So this is the analog output configuration, and in turn, after reading these signals, this controller will run the control algorithm and it will give out the PWM through digital output, and that needs to be fed to digital input of the simulator. So you can see here I have a digital in. This digital in block will read the PWM generated by the external controller, and that is fed to the inverter inside. So inside the subsystem you have the inverter, and you can see all the 6 PWMs are taken from digital input and it is fed into the inverter. So this is how you modify your simulation in such a way that it is ready to be tested in HIL. So you go through the basic procedures I said, grouping into subsystems, changing the solver and all those stuffs, and you configure analog outputs and you configure digital inputs for this application. So now this is what plant model is all about. Now I will go into the controller model. Controller OP8666. This controller, it is nothing but inside the controller you have the TI F28379D card. So to run the models in this controller, you need to inside this controller you need to first install the MATLAB C2000 add-on. So there is a library add-on in MATLAB which you will find, which is specially for the Texas Instruments C2000 control boards. So you need to install that, and you need to take some custom block sets. So the first step in your controller model is, you have the control logic here. This is the control logic. Inside it you can see. So this control logic and the plant is developed by one of the students of sir. Now to run it in this controller, you need to additionally configure the analog inputs here on the controller. That means ADC. You need to configure ADC modules in the controller. ADC is the one which helps you to configure the analog inputs of the controller, and it will help you to bring the signal which you have outside into the controller. So you can see the ADC modules here. See, I have the ADC modules here with I have around 3 plus 4. Yeah, I have around 7 ADC modules because we have a total of 7 signals. We have 3 voltages and 2 currents before filter and 2 currents after filter. So that's what this ADC module is all about. So when you are configuring ADCs, you need to make sure that which ADC modules controls which channels in your controller. So we do have a few pin diagrams for that. Accordingly, you need to configure ADC, because if you see inside it, each ADC will have different modules A, B, C and D. So which module you need to configure will depend on what channel you are using. So all those steps this controller has its own pin diagram configuration. So accordingly you will be able to configure it. And after configuring the ADC, here you will get the signal, but this signal is again it is the ADC output. It is still not your real signal. So you need to do again some you need to again add some gain factors and offset factors, because inside this circuit we do have some offset circuitry and gain circuitries. So to bring back the original signal from this ADC signal, you need to once again have some signal conditioning here. You can see I am adding some offset and I am adding some gain values here. This offset and gain is something hard coded and it is fixed for this controller. So whatever signal you are trying to take from your external analog input, you need to multiply with these gain and offsets so that you get the actual signal after that. It will also depend on your the resolution of your ADC, like whether it is a 12-bit ADC or 16-bit ADC. You need to configure the gains accordingly. So these are hard coded values, which is particularly for this OP8666 controller. So this will depend on for other controllers. So you need to go through the manual of that controller and you need to find what is the offset, what is the resolution of the ADC, all those steps you need to find, and then you need to do the math to get the actual signal from your ADC module. So here you will get all the signals which, so now whatever signal, these signals will come from your OP5700 simulation now, because from the analog out we are connecting it to analog in and we are retrieving the original signals here, and these signals will go to this controller. You can see inside this you have the control logic happening, and this controller will further give you the duty ratio or the modulation signal. So that modulation signal you feed it to this PWM block. So again this PWM block is something which is particular for this 28379D card, the TI278, the TI card which you have here. So this block will come from the same C2000 library which you will install in the MATLAB library. So you will use this PWM module to generate the PWM. Now this PWM will go to the digital output of the controller which you have physically here. and that will be physically routed to the digital input of your Opal RTM 5700 simulator through the connection which we have here. So in hardware perspective, we have two connections: analog output from 5700 to the analog input of the controller, and digital output of the 8666. The controller is connected to the digital input of this 5700 simulator. So these two connections you have, and yeah, this is what the control model is all about. So now we have the control model and we have the plant model. How do we run it? So for running the controller model, we are going to follow the automatic code generation option which is there in the MATLAB. So that is the advantage of using this TAC 2000 board. So you can just click this build option here. The moment you click the build option here, automatically MATLAB will generate a code for that, and you need to launch Code Composer Studio. So Code Composer Studio is a software made by TI specifically to dump codes onto the TI cards. So in MATLAB itself, you will have an option to launch Code Composer Studio. You can see here, open Code Composer Studio. You can have that. You can see that link. Through that, you will launch Code Composer Studio, and this window will open. So here you will have the automatic code which is generated. You can see here. So now using this Code Composer Studio software, I'll be dumping it onto the controller. So here you have the debug option here. If you click the debug option, the code will be loaded onto the controller. Let's wait. Okay, parallelly when it loads, I'll also show you our RTLab environment. So when the code loads, I'll show you this one. So this is the RTLab software which helps you to run your MATLAB models into this simulator which you have here. So in RTLab, you have three options. You need to first import the model. I already have the model imported here. You can see there that sign limiter, whatever. So that is the model which I have imported. So you need to build, load, and execute here. So you have the build option, and you should also add the target. The target is your simulator. Every simulator comes with its own IP address. So your host PC will communicate to the simulator through this, through the LAN cable. So you can, the advantage here is you can keep the simulator over the network, and you will be able to access the simulator from anywhere, anywhere in your, anywhere whenever you are connected to the network. So that is why you add the target here corresponding to your IP address. So that is the IP address, but you add the target, and then after adding the target, you bring in the model, you build, load, and execute. So building is the stage where the model will, the RTLab will generate the code, and loading is the stage where it will dump the model, and execute means model will execute. So anyhow, I have already built, loaded, and it is executing. So the build, load, and execute options are here, as you can see. Now all those options are grayed out because I have already done it to save some time. Now you can see the model is running here, but now the controller is still not loaded. So let's go and run the controller, and then we'll come back here and we'll see how the results are. Yeah, so here the controller is loaded. I'll just run it. So here I have added the control variables here in CCS. All the analog inputs which I am reading, all those stuffs I have added it here. Now you can see all those variables, all those variables are reading a unit sine wave. If you see the value in this section, it is toggling, it is varying from -1 to +1, because currently in order to just test whether the analog inputs are working properly or not, I am just forcing some sine wave to see if it works or not. So that is what it is. Currently you are reading the forced sine waves. Now in the plant model, I will be switching to the actual feedbacks of the inverter. See here the plant model is running. So here I have the option to switch between the forced signal and the actual signal. So now we will switch to the actual signal. So now the actual plant feedbacks are going to the going to the controller. So now you will see the control happening. You can see the grid voltages and grid currents here. So there are two ways to monitor. Again, you can either monitor it through the scope which you have here, or you can also monitor it through RT Lab. Maybe I'll show you that first. Let the scope open. You see the voltages and currents. You can see the sine waves here. You can also monitor it through software from RT Lab called Scope View. So normally I use that for seeing it. Now I'll launch that and I'll show you all the three results. I mean, I'll show you the grid current, grid voltage, and also the inverter's current. All those three we can see now.
So you have 5 minutes.
5 more minutes? Yeah, we can wind it up. So this is my contact. This is my email ID. If you want, you can note my email ID, and I'll be happy to respond to all your queries. So
Okay, so I know there are so many questions, but due to time, we'll keep it for later. But you have already contact number of him, or if you want to know more, you can also contact me. And yeah, so this is basically one demo. So you can think of, let's say you have a DC-DC converter control also. You can add to the plant model and also create the pulses through the 8666 controller for that also. Okay. And thank you so much, Siva, for your time and agreeing in this short time and coming here. And at least people are more interested to real-time simulation. So be ready, you will get more questions.
yeah, I'll be around. You can reach me
Yeah.
at any time.
So he will be in the lab in the afternoon. So any connection, anything you want to see, you can see after the closing ceremony. So thank you.